In this next section, we're going to look very briefly at the solid state of matter. So most of the time so far, we've talked about liquids and how to go from gases to liquids to solids and vice versa. But solids are also really interesting. Now, solids, this is a huge topic, and we're not going to be able to do justice to it. But let's try to have some overview and kind of get some examples of what you could see if you look more at this in the future. So when it comes to all of the solids that science knows about, there's two forms. One is called crystalline, and in a crystalline solid, all the particles are in a highly ordered arrangement, and they're repeatable. So the part at the left would be the same as the right, which is the same as the top and the bottom, stuff like that. There's also a huge type of solid category called amorphous solids, and amorphous solids don't have a particular order in arrangement of particles, and these will be things like clay and dirt and stuff like that. We're only going to focus on crystalline solids in this section because we're kind of limiting here what we can do. Crystalline solids have repeatable patterns, so it makes them a little bit easier to talk about, honestly. But amorphous solids are very cool, lots of neat uses for it. It's more than we're going to get into in this part of Chemistry 222. If you have a crystalline structure, the molecules, atoms, ions, whatever you're talking about, are locked into what's called a crystal lattice. And crystal lattice are these small repeating units that go over and over and over within the solid. And they're very, very strong. That makes solids basically incompressible. So liquids you can't compress very well. Gases you can compress really well. But solids are almost impossible to do anything with. They're going to be there. Very rigid. You'll have cleavage lines where they break off, but you won't be able to change them. Pretty cool. Unit cells in all of the world's known solids can be broken down into 7 types. They call them the Brevis lattices, or unit cell types. And the names of them are there: cubic, tetragonal, orthorhombic, etc., etc. In this class, we're only going to look at cubic unit cells. And the different properties of all of them are listed there on the left. But if you look at the top one, that's the cubic unit cell. And we're focusing on cubic cells because of 2 things. First of all, the lengths of all sides of these cells are the same. So A and B and C are all the same length. It's a cube. Also, the angles that are within that particular model are all 90 degrees. And that honestly makes the math a lot easier. So we're only looking at cubic unit cells. We're only looking at crystalline solids. So you can see we're really limiting ourselves here to what we're looking at. But again, this is just a crazy section, and we're going to keep it somewhat simple. So we're going to talk in this section about simple cubic, face-centered cubic, and body-centered cubic systems quite a bit, all right? But I want you to know that outside of our little Chem 222 world, there's lots and lots and lots of different variations here, and we're just barely touching them. But this will give you an idea of how this works, and if you have to work on the other systems in the future, you absolutely can. So there are 3 types of cubic unit cells, and all the 3 types I'm going to show you here, they all have similar lengths. So length, width, and height, they're all the same value, whatever it is. Also, the angles are all 90 degrees, and that makes the math a little simpler. You don't have to use sines, cosines, stuff like that. And the 3 types are called simple cubic, which we'll abbreviate SC. A simple cubic cell just has an atom in each corner of the cell. So there are 8 corners in a cube. Each of them has an atom there. That's called the simple cubic, and it is the simplest one, as we'll see. The next one we'll talk about is called a body-centered cubic, or BCC. Now, body-centered cubic is the same as the simple cubic. There's an atom in each corner. However, body-centered cubic has, if you look carefully, 1 atom in the middle of the cube, in the body of the cube. So body-centered cubic is like simple cubic with 1 atom in the middle, and that'll be important to us here in a little bit. The last kind is called face-centered cubic, FCC. FCC is like SC, simple cubic. There's 1 atom in each corner. But if you look carefully, every face of the cell has an atom in it. Now, a cube has 6 faces: top, bottom, left, right, forward, backward. Each of those faces has an atom in it. Does not have an atom in the middle like the body-centered, but there is one in each face. So simple cubic, body-centered cubic, face-centered cubic are the three types of unit cells, and we'll see how they can be used to describe the properties of metals and stuff like that.
A simple cubic unit cell has one atom at each corner of a cube. The cells stack together to form a solid crystal, the overall shape of which has square edges. Each ion is shared by 8 different but connected cube cells. The arrangements of body-centered cubic and face-centered cubic unit cells are similar but more complex.
We'll talk about these unit cells a lot here in a little bit, but just remember in the back of your head that all of these are just the smallest repeating unit of what you would see in a sample of the substance you're talking about. So if we talk about, for example, the copper cubic unit cell, we'll talk about one of these little unit cells, and that will repeat over and over and over again in a sample of copper. Remember, in any sample, you're going to have 10 to the 23rd or so Avogadro's number worth of atoms, but on the smallest level, they all repeat. They'll all be in these same patterns. So on the upper right-hand side there, you can see, especially on the right, that little tiny atom that's there in the middle is actually connected to 8 different cells, all right? There's 8 little cubes that it belongs to. It's not part of just one cube, but it's actually part of many, many different cubes. And so in the unit cells, like in the lower part there, the kind of green part there would represent one cube. But each of those central atoms, those corner atoms, is actually part of other cubes as well. So we'll see how this all fits together. It's pretty neat how Mother Nature makes these repeating units, and we can use this then to understand the properties and stuff like that. The simple cubic unit cell is literally just where you have an atom in each corner of the unit cell. But you can see on the left-hand side there's 2 representations. The top part shows the actual atoms, which are basically spheres. The bottom part, though, is important. It shows what this unit cell would look like if you take, if you will, like a chainsaw and cut off all the parts of those atoms that aren't in the unit cell. And what you see right now in that video, that shows the chainsawed parts that are left, all right? And you can see that those atoms, even though it's a whole atom, only 1/8 of the atom is still in the unit cell. And the other 7/8 of the atom belong to different unit cells that repeat over and over and over again. So one thing that chemists talk about is how many net atoms are in each of these unit cells. And each of the simple cubic unit cells represents 8 atoms, but only 1/8 of them are inside. So 8 times 1/8, each simple cubic unit cell is 1 net atom. You have 8 times 1/8 atoms, which is 1 net atom, which is pretty cool. That's why sometimes people like these chainsawed versions, if you will. It shows only the 1/8, which is inside the cell, and since each corner represents an 8th and there's 8 of them, that's 1 net atom. The other thing we'll talk about when it comes to simple cubic unit cells is the ratio between the edge and the radius. And for the simple cubic unit cell, the edge of a cell equals 2 times the radius. And you can kind of see this one visually because when you cut off the parts that aren't there, like you have like 1 radius there on the top and 1 on the bottom, and they touch, so the edge, which is length, width, or height, either one because they're all the same, the edge equals 2 times the radius. In the lab, the solids lab, there's some more descriptions as to how this all works out if you're curious. If geometry is your thing, this will be a section for you. It'll talk about how the edge is equal to 2 times the radius, etc., etc. But punchline, at the end of the day, when you hear simple cubic unit cell, think 2 things. Think 1 net atom per simple cubic cell, and also think edge equals 2 times the radius of the atom. Those 2 things will help you go forward. The body-centered cubic is similar to simple cubic. There's one atom in each corner, but there's also an atom in the actual central part of the cell. So if you use the chainsaw on it, you have the 8 times 1/8 corners like before, but you still have that one atom in the middle. So when scientists talk about the number of atoms in a body-centered cubic, it's not only 8 times 1/8 of the simple cubic, but you also have one in the central. So there's 2 net atoms per unit cell. I'm not going to go into the geometry of how the edge to radius ratio was figured out, but when you do the geometry, the edge of a body-centered cubic unit cell equals 4 times the radius divided by the square root of 3. And you can check out the lab for more information on that. Body-centered is a little bit more common than simple cubic because you end up with 2 net atoms per cell instead of 1. It's a more efficient type of packing, and the more efficient it is, the more atoms you get in, it's better. We'll talk more about this in the solids lab. The face-centered cubic unit cell is also known sometimes as the cubic close packing cell, and there are subtle differences between FCC and cubic close packing, but we're not going to worry about them in our class. When you take the chainsaw to the face-centered cubic, you still have the 8 times 1/8 atoms in the corner. But the difference now is the face atoms, half of the atom is in the unit cell and half of the atom is outside the cell. So when you want to know the number of atoms in a face-centered, you have 8 times 1/8 for the corner atoms as before, but now you have 6 faces, and each face has half of an atom left once you take the chainsaw to it. So 6 times 1/2 are the number of atoms in each face. 6 times 1/2 is 3. And you add that to the 8 times 1/8 atoms in the corner, which is 1. 3 plus 1, 4 net atoms per FCC unit cell. And the edge to radius ratio for FCC is edge equals 4r divided by the square root of 2. And you can look in the solids lab for more information on that if you're curious. But again, punchline, when you hear FCC, think 4 atoms per cell, and edge equals 4r divided by the square root of 2. Here's a problem you might see. It says the unit cell for a metal is found to have 2 atoms per unit cell. What kind of unit cell does this represent? And there's all those different choices right there. Well, if you remember from what we just talked about, simple cubic, answer A, is 1 atom per cell. Answer C, face-centered cubic, is 4 atoms per cell, and face-centered cubic is the same, for us anyway, as cubic close packing, the CCC, answer D. But body-centered cubic, BCC, that has 2 atoms per cell. So the answer here would be B. BCC, body-centered cubic, 2 atoms per cell. Simple cubic, 1 atom. Face-centered cubic, 4 atoms. CCP is for us the same as FCC. There's actually differences, but we're not going to go into it. Good to go. The metals on the periodic table often fall in one of these categories. So simple cubic is very rare. It's only in polonium, which is quite dangerous and stuff, but it is actually simple cubic. Body-centered cubic, almost all the alkali metals and some of the alkaline earths and a couple of the transition metals use body-centered cubic for packing. But by far the biggest one is face-centered cubic. Now, face-centered and hexagonal close packing, which is also close packing, the CCP version, is what most of the metals are. But again, most of the metals fall in one of these categories. So by studying these types of unit cells, you can represent the bonding and the patterns for the different metals. Most of the metals on the transition metals, not all of them, all right, like manganese and lanthanum there, and mercury for that matter, have their own things going on, but a lot of them fall in one of these, which is kind of cool. They use X-ray crystallography to tell the unit cell types. And X-ray crystallography is a fantastic phenomenon. An X-ray is created. It's sent through what's called a double slit to create basically like a line of X-rays. And when they send the line through a crystal of these solids, a pattern emerges on like a piece of photography paper, like a picture. And they can interpret that back into the unit cells of face-centered cubic, body-centered cubic, and simple cubic. It's a fascinating process. It's definitely more than we need in Chem 222, but but it is how they use it, and it's a very well-established pattern. If you're an X-ray crystallography person, you will have the opportunity to join many research groups. You'll do the X-ray work for them, and you'll be added into research papers. It's pretty cool. So let's look at an example of how you can find out if a metal is simple cubic, body-centered cubic, or face-centered cubic. And we'll use this example with aluminum. And aluminum has a density of 2.699 grams per centimeter cubed. The radius is 143 picometers, and we can actually use this information to verify that aluminum is face-centered cubic. All right? Now, at first, this might seem like a daunting problem, but it basically comes down to unit analysis, and we'll talk about some strategies to solve these in the solid lab. But if you look back at the face-centered cubic system, there are two important aspects of FCC, and the one we're going to start with here is edge equals 4 times the radius divided by the square root of 2. All right? It also, FCC means 4 atoms per cell, and basically what we're going to do is we're going to use the edge to radius ratio and then solve for how many atoms are inside the unit cell. Start with 4 times the radius divided by square root of 2. The radius is 143 picometers, which is very small. 4 times 143 divided by the square root of 2, 404 picometers. Now, in the next step, we're going to take the edge and we're going to cube it, because edge is length, and length times length times length equals volume. But because these are cubes, length, width, and height are all the same. So edge, which is length, edge cubed equals volume. We're going to turn this edge into a volume. But if we do an edge in picometers and we cube it, we're going to get a volume of picometers cubed, which is quite crazy to deal with. And if you look at these values, density is in centimeters cubed. So what we're going to do first, before we cube it, is we're going to take that edge and turn it into centimeters. Now, a pico is 10 to the minus 12. So a picometer is 10 to the minus 12 meters. That would allow you to go from picometers to meters. And then a meter is 10 to the minus 2. So a centimeter, 10 to the minus 2 meters. I'm skipping the meters in this conversion. I'm going directly from picometers to centimeters. And when you do that, it's 10 to the minus 10 centimeters per picometer. And I recommend that you kind of work through that so you know how this all goes. But at the end of the day, 404 picometers is 4.04 times 10 to the minus 8 centimeters. Now that we have an edge in centimeters, edge cubed equals volume. As long as the length, width, and height are all the same, you can just cube the edge to find the volume. So 4.04 times 10 to the minus 8 centimeters cubed in your calculator is 6.62 times 10 to the minus 23rd centimeters cubed. Cubed is usually on your calculator. There's different ways to do it. You might have a y to the x button, which will allow you to do it. Also, if you have what's called the caret, which looks like an arrow pointing up, you can go caret cubed to do that. Figure out how to do this process. It will be handy in this particular section. And if you cube 4.04 times 10 to the minus 8, you'll get 6.62 times 10 to the minus 23rd. It's a nice way to kind of check yourself. This volume is very small, but even though it's small, we can use the density, which is given, to find the mass. So we're going to take the volume we just calculated and multiply it by the density. The centimeters cubed cancel. 1.79 times 10 to the minus 22 grams per unit cell. And again, that's pretty small, but these unit cells are pretty small, so it's kind of interesting. The molar mass of aluminum is 26.98 grams per mole, and Avogadro's number is 1 mole per 6.022 times 10 to the 23rd atoms. And if you take these numbers, you can see that the mole is a common denominator. So what we're calculating for right now is the number of grams in an atom, the mass of grams in an atom. So 26.98 divided by Avogadro's, you get 4.480 times 10 to the minus 23rd grams. And that's the grams per atom. And again, pretty small, but this is actually something you can do with math. Woohoo, math is fun. Anyway, that's the mass per per atom. So earlier we saw that there was 1.79 times 10 to the minus 22 grams in a unit cell. And what we just calculated here is that one atom of aluminum, 4.480 times 10 to the minus 23rd. And when you multiply these together, you can see that you end up with atoms per cell. The grams cancel out. It comes out to be 3.99, which is awfully close to 4 atoms per unit cell, FCC. So we have just verified here that aluminum is a face-centered cubic. If we would have come up with a different number of atoms per cell, it would have been not face-centered cubic. But 4 atoms per cell means it's FCC. Pretty cool. So this gives you a kind of an idea how these problems work. The one thing I want to highlight is that you'll usually have a radius in picometers, sometimes angstroms, whatever. You want to convert those to centimeters before you cube them, because it's much easier dealing with centimeters cubed than it would be picometers cubed or angstroms cubed. And again, we'll talk more about this in the lab. There are many other types of crystalline solids, though, besides the metallic ones that we just talked about. There are ionic solids, covalent network, molecular, all different kinds of things. So diamond, as an example, is a covalent network kind of system. It's really crazy. So we're only looking here at crystalline solids, and it ignores all the amorphous ones. And we're only looking at the cubic unit cell ones, too. We're ignoring all the other types. So again, this is a very primitive introduction to solids, but you kind of see what's happening. Almost all of them break down to some, at least the solid crystalline ones, break down to some kind of small repeating unit, and from there you can make predictions on it. It's pretty cool kind of stuff.